Archimedes told us that a body submerged in a pool experiences a buoyant force, which is equivalent to the weight of the fluid displaced. And if you go back to earlier videos, we show that that is indeed the case by integrating the pressure from the bottom and from the top. And in fact, it is such an insightful concept from Archimedes, because it means that we don't compute the buoyant force by doing the integral of the pressure and the very complex shape of a body. We just look at its volume, and we take that volume by the unit weight of the displaced fluid, and we compute the buoyant force. Then came Pascal. Pascal basically tells us that if we go to a swimming pool and we go deep in the swimming pool and we feel the pressure in our ears, and then we turn the head around and we feel the pressure in the ear, the pressure is the same. In other words, the fluid pressure in the X is equal to the fluid pressure in the Y, which is equal to the fluid pressure in the Z direction. And these were sufficient to solve a wide range of problems in hydrostatics. But when the fluid begins moving in the body, now we also have to consider the interplay between all the contributions to energy. And so we have to look at the whole energy in the system, and that is what Bernoulli contributed. And he said, what is the total energy? Well, the total energy, remember from mechanics, is the kinetic energy plus the potential energy. And if it is a fluid, it will be plus the energy in the pressurized fluid. So this is, the kinetic energy is 1/2 mass velocity squared plus the potential energy is the weight of the body times the elevation of the body plus pressure times volume for the energy stored in the fluid subjected to pressure. If we divide both sides by the weight, then the energy per unit of weight will have dimensions of, this is Newton times meter over Newton, so it has the dimensions of meters, so we're going to call this a total elevation, which is really the energy per unit of weight of the fluid. So dividing here by weight and here by weight cancels out, and here by weight, then we conclude that the total energy in terms of height per unit, in terms of units of length, is going to be, notice that weight over mass is g, so is 1/2g velocity square plus h elevation plus this weight per volume is going to give me the unit weight of the fluid, so it's pressure per unit weight of the fluid, of water in this case, or any fluid. Please notice that this is dimensionally correct, so all these are in units of meters, so we can summarize by saying that the total energy is equal to the energy due to velocity plus the energy due to the elevation of the body with respect to a datum, plus this is also an elevation due to pressure. In general, when water seeps through soils or fractured rocks, or this could very well be, for example, oil seeping through a contaminant, this velocity is going to be quite small. The contribution of energy due to velocity is quite small, and so the equation simplifies. In most cases, it simplifies to H total is equal to h elevation plus h due to pressure. That is for the velocity that goes to 0. But this is not always the case. Let me give you an example. If you are drilling a borehole with mud, and at some point you hit a fracture, and you experience what is called loss of circulation because the mud doesn't come up, it just goes through the fracture. When that well hits that fracture, the velocity is so high that you cannot discard this contribution. And in fact, very weird things happen. If you actually measure the pressure along this fracture, you will see that the pressure it has a transition, and the pressure decreases. In other words, flow is flowing opposite to the direction of pressure, even in a horizontal fracture. So we cannot always disregard this component, and this is particularly true in very highly permeable systems near the injection well, where the velocity components are very high. Otherwise, in soils, beneath a dam, beneath a foundation, near a retaining wall, this component will be disregarded, and we're using this simpler formulation. The next one is a relationship between the gradient that is driving the flow and the velocity of the flow, and this was advanced by Darcy. And at small velocities, in the small regimes, we can assume that this is a linear relationship. Notice that linearity is so extensively used in engineering, from Ohm's law to Hooke's law, and also applies to Darcy. And so the velocity of the flow is going to be the hydraulic conductivity of our soils times the gradient. And you may wonder, what gradient? Because now we have different components. We have the total energy, the elevation, the pressure. And so if you look at the river going down, flowing down, you say, oh, of course, this is a gradient of elevation. That is true, but at the same time, when I'm filling up a tank with a pipe, I'm pushing the water up because I apply high pressure. So you may be tempted to say, oh, this is a gradient of pressure. But let's consider now a swimming pool. And in a swimming pool, now if I take this point A and this point B, and I take the bottom of the swimming pool as the datum, the reference, therefore this is the elevation of point A, H elevation of point A, and if I place here a pipe and I see how high the water goes up in the pipe, this is the water will go up to the top of the surface because of equilibrium and communicating tubes. Therefore, this is H pressure at point A. Now I can do the same with point B. This is H elevation for point B, and if I place a pipe here, by communicating tubes and equilibrium at the base, I convince myself that the water will rise all the way to the water level in the swimming pool. Therefore, this is H pressure at point B. Using the geotechnical concepts, you can think of this pipe as a piezometer. So every time you think of the pressure head, you may also want to think, how high does the water rise in an idealized, a hypothetical piezometer at that location? So P stands for pressure, but as a physical model, think of a piezometer. And so, look folks, if elevation drives the flow, water should be flowing from point A to point B because point A is higher than point B, according to the river. However, the water is not flowing. Now, if pressure drives the flow to fill up, in this case, the tank, if pressure drives flow, then point B has higher pressure than point A, so fluid flow should be happening from point B to point A. But there is no fluid flow in a static swimming pool. And the reason is because these 2 points, A and B, have the same total energy. Is elevation plus pressure is the same at point A as elevation plus pressure is for point B. In other words, let's never get confused that velocity of fluid flow is controlled by the permeability, and the gradient is a change in total head with respect to length. It's the total energy that drives the flow. Let's consider next an element inside the soil mass where fluid is coming in the z direction and in the x direction, and fluid is going out, qx, plus there has been a change in the flow rate, so there is a change in qx dx times dx, and that will give us the next value of the outflow, and the same in this direction. So this is a qz plus a change in the flow rate in this the gradient of the flow rate in the z direction times dz. If we are going to conserve mass, and if the fluid is incompressible, and that is very important to recognize, then we can say that qz plus qx, which is all the flow going in, has to be equal to all the flow going out, which is clearly, this cancels out. And now we can replace Q by Darcy's law, where we can also explain Darcy by saying that Q is equal to velocity times area, therefore it's equal to KIA. So if we do the replacement, now I get that the derivative of Qx implies that I'm going to have a variation not only in the gradient but also in K. So it's d of the permeability in the x direction, the gradient in the x direction over the x, and this is times the x, but this flow rate is taking place against the area here, and the area is going to be equal to dz dy. So then I have a dx dz dy, and I have the same with the next term, which is plus the partial of kziz with respect to z times dz, and the flow rate, and the flow is taking a place against an area A, which in this case is dy dx. And this is equal to 0. Therefore, I can multiply both sides by the inverse of the x dy dz, and this cancels out. And this is Laplace's equation for the case that I have not only changes in the gradient, but also changes in permeability. Before we proceed, I think that we need to make very important observations here. Observation number 1, this was really a mass conservation equation which we converted into a flux conservation. That means that the unit weight of the material remains constant. That means that the fluid is incompressible. Second, we assume that everything that goes in comes out. That means that nothing stayed here. For example, if the soil was unsaturated, part of the fluid going in could have remained there and not coming out. So we are assuming that the soil is saturated, or that there are no changes in saturation. Next, we are making one more assumption. we're making the assumption that the body is not changing its volume. Because if this was a sponge, I could be squeezing the sponge at the same time, and probably more fluid would be going out than the fluid that comes in. That means that we are saying that the matrix is incompressible, or that the pore structure, in this case the solid skeleton, and that is not changing the volume. So these are important assumptions underlying this equation, and if any of them do not apply, we have to go back to the beginning to put the right terms, as we will do when we do the consolidation equation. Now we're going to make one more assumption. If the permeability is isotropic, then this implies the following: 0, I can get the kx and kz out, and I multiply by the inverse of them, and they disappear. So now I have that the change in the gradient in x, or the gradient of the gradient in x, and the gradient of the gradient in y add up to 0. What this tells me is that replacing the gradient by dh dt, this results in the second of h total with respect to x twice, plus the second of h total with respect to z twice is equal to 0, and that is a Laplacian, and that is Laplace's equation. And you can generalize it in 3D by adding the second of h total with respect to y twice as one more term. This would be in 2 dimensions. And so we finally got to Laplace's equation, which is the one that we have just highlighted. In a more general way, we can create a higher order set of equations, which are the Navier-Stokes equations. And this is French and Irish researchers who developed the whole formulation, and which can also account for compressible fluids, etc. But for the sake of our applications, this is a sufficient set of equations. With this set of equations, now we're going to solve a large number of situations and analyze a large number of situations in the geotechnical field. And these apply all the way from near surface applications to deep in the seafloor, as well as in geological formations for oil and gas or CO2 geological storage. So what are the typical type of exercises that we are going to do? We need to start by solving this equation, the Laplace equation, because that will tell us how the energy varies throughout the system. And this is a differential equation, and the first thing that we need to do to solve a differential equation is to define the boundary conditions. In other words, what is the total energy at the inlet, what is the total energy at the outlet, and flow boundary conditions. Whether we solve this numerically or graphically or analytically, we must start by carefully understanding what are the boundary conditions of our problem. So the first thing is to obtain H total as a function of, let's say, x and z. Once we know the total head everywhere in our system, once we solve this differential equation and we know the energy throughout the space of interest, now we can solve many other problems. For example, we know that fluid flow, the flow rate, is the gradient of the total energy times the permeability. So now we can solve the flow rate, which is k dh total, the length in some direction times the area. And for example, we are going to use this to design pumps. How much flow we need to remove out of an excavation, or how much flow will leak out of a dam. Now, we know the total head from solving Laplace's equation, And we know the elevation just by measuring with a ruler. For any system that we have, we know the elevation of every point. So if we know the total head and we know the elevation, now we can compute the pressure head, because H pressure is equal to H total from Laplace's equation minus H elevation from the geometry of our problem. Now, H pressure, if you go back to the derivation of H pressure, was the pressure divided unit weight of water. That means that pressure is equal to H pressure times the unit weight of our liquid, in this case, let's say the water. Now, if we know the pore fluid pressure, which should be predictable if you actually have a piezometer, you should be able to corroborate this. Now, we know something very important for the mechanics part, because sigma effective is equal to sigma minus u, and this is the pore pressure that comes into this equation. Furthermore, we know that tau ultimate, the shear strength of the soil, is going to be equal to sigma effective tangent phi. And this is the beauty of solving these type of flow problems, not only for the point of view of assessing flow rates, but also from the point of view of assessing stability of our geotechnical systems.